Okay, great. Should I just get going?
Yeah, you can go.
Yes. Hello, everyone. I'm sorry I can't be there in person, but today I'm going to talk to you a little bit, or just give you an overview of the different types of mixing that occur within the Arctic Ocean and how our knowledge has changed about what we understand of how this is happening. As you probably have heard, the Arctic is changing at a really fast rate, and one of those changes is the greening of the Arctic Ocean. As you can see here, actually what that means is that the permafrost is melting and there is more kind of green vegetation becoming kind of dominant in Arctic ecosystems on land. But this is also true, it turns out, in the ocean. We're seeing increases in primary productivity. This is data from a satellite observations that were made from 98 to 2012, and they really showed that, oops, this has gone backwards. They really showed that, can you see a mouse or my mouse?
Yes, we can.
Okay, good. All right, so I can use that. This really showed that there's really enhancement of primary productivity on the shelves and around the margins of the Arctic Ocean, as seen by satellites unusually in the global oceans that are experiencing, as we all know, climate change. This is also true if you look at model predictions for the future. And here you have, again, net primary productivity shown in the colors. These white line picks out the margins of the Arctic Ocean. And this kind of inspired, these sorts of predictions inspired a project that I led a few years ago. And of course, here, all my co-conspirators, because of course I didn't do all this work by myself. And this will give you an overview of our project, which was known as Peanuts, or rather we were questioning whether primary production was driven by escalating Arctic nutrient fluxes. And so this is where the mixing comes into it, because I should say that the enhancement of the primary production observed by the satellites was not explained simply from the reduction of the sea ice. Of course, when sea ice goes away, more of the ocean is exposed to solar radiation and allows for greater photosynthesis. But the reduction of the sea ice alone could not explain the increase in primary productivity. So we set out to measure ocean mixing and nitrate fluxes and looked at ecosystem response from models and satellite measurements. So what I'm going to show you now, and here's nice pictures of all my co-conspirators, is a schematic section of the Arctic Ocean showing you all the different water masses as you go through the Arctic, from the eastern side of the Arctic in Fram Strait, where you have inflowing Atlantic water, to the western side of the Arctic, where you have an inflow of Pacific water in through Bering Strait. All right, and this is oriented with the Atlantic on the right-hand side. And so here we have this schematic, and this schematic shows you, in the first instance, a few kind of processes that are picked out here. And for many years, certainly in the 90s and before, we thought that the Arctic Ocean was generally covered over by perennial sea ice, and that was true for many years, in which kind of slower processes, such as lateral intrusions from the sides, as the different water masses encounter each other, such as the warm, salty Atlantic water encountering kind of Arctic source waters in the surface and below, kind of interact. And so you get the growth of lateral intrusions, which are driven somewhat by double diffusion on the top and bottom edge. And double diffusion, of course, is a really kind of slow mixing process, which is picked out by characteristic, and here are some profiles of temperature and salinity from the Eastern Arctic, taken in 2007, 2008. And these profiles really show you the kind of warm, salty Atlantic water, which is sitting subsurface. And so you've got this subsurface maximum in temperature. And it's, of course, saltier than the surface waters. This was 2007, you may recall, was one of the minimum sea ice years. And so actually the surface in September was very warm. But other than that, below you had kind of business as usual. And if you were to take a close-up of the temperature and salinity profiles, you get these characteristic staircase structures. And these develop, of course, because you have a mixing process or vertical mixing process, which is sort of reliant on the diffusion rates of heat and salt. Heat diffusing much faster than salt, which kind of reinforces these staircase structures, as it were. Anyway, these are really slow processes. And if you were to look at kind of the differences, so I need to, here we go. If you were to look at the differences in what is an Arctic boundary current of the Atlantic water flowing along the boundary comme ça, like so, and we were to compare the differences between the heat content in the Atlantic water from this kind of section to this section, or this section to that section, we really had double diffusive heat losses, which, as you can see, were an order of magnitude too small to account for the changes in the heat content difference between these sections. So this really reinforced the notion of the Arctic as what must be fairly a quiescent basin, not very much vigorous mixing because you can't get wind energy through the sea ice cover, or you know, with deep basins, you don't get a lot of tidal mixing, whereas on the shelves, and this is what we assume, that this difference must be driven by exchange with the shelves, where you can have, say, more vigorous tidal mixing in the traditional sense. And what we were able to show, how we go forward, is that when we were starting to look a bit more at the tidal mixing and look at all the kind of, wait, am I going forward? Here we go. Tidal mixing, what we were able to show is that actually along the basins, and this is not a picture of that, but this is a picture of reinforcing that idea of a quiescent basin here, where we made dissipation measurements right in the middle of the Arctic. And what this showed here was during the 2012, another sea ice minimum year, where we had a great big anticyclone, a great big Arctic cyclone, as it were. It was called the Great Arctic Cyclone 2012. You can see the wind going crazy bazonkas here in the pink from the shipboard observations. There was no ice. There was excitation of really extraordinary currents, as shown by the mooring data. And there was higher dissipations, I guess, but the dissipations didn't really match. As you can see here, the dissipation enhancement didn't really match where you got the big win in energy input during this time. So the idea in the early kind of 2000s and 2010s that the Arctic was a quiescent basin, and that even as we were starting to lose the ice, the addition of sea ice melt, fresh water at the surface, was enhancing the stratification in a way as which to suppress the basin suppress the mixing, the energy required to mix these water masses. We weren't getting enough energy in because the stratification was so well enhanced in the basin. But along the margins, the picture is a little bit different, because here along the margins itself, you can get tidal mixing along the edge of the along the continental slopes. And what you find is that if you were to look at the energy that comes out of the barotropic tide and must go into internal processes, in blue, this kind of matched relatively well with the picture of what we had in direct measurements of turbulent mixing. So this pattern shows that turbulent mixing of Atlantic water on the slopes did correspond with the dissipation of the tides, except for this date here, which was these green profiles here, which occurred during the Arctic cyclone. So we had this traditional picture of enhanced mixing along the continental slopes, but what's really interesting is that this tidally driven mixing actually has to occur via a slightly different process, particularly on the slopes, than what you encounter at lower latitudes. And of course, mixing this kind of warm, salty Atlantic origin inflow water up is enhancing sea ice melt, because you can provide heat to the surface from this subsurface water mass. And the reason in which the mixing or tidally driven mixing in the Arctic is slightly different from elsewhere, of course, is that within this green circle here, and we're looking down on the Arctic from above the North Pole, the arrows, the red arrows show you the pathway of the Atlantic water, and the orange arrow shows you the pathway of the Pacific water. And what you can see is that within this region here, we are above the critical latitude for propagating internal waves generated at the M2 frequency. So M2 is the twice a day semi-diurnal frequency, where you have lots of tides kind of swishing back and forth across seamounts, along continental slopes. And in many places, this generates an internal tide that can propagate away and take the energy with it. But because we are above the critical latitude, and by critical latitude, it's the kind of internal frequency of the ocean, the inertial frequency, kind of matching the tide, internal tide generating frequency, you can't get propagation of these waves. And so you can get the generation of internal tides, but what we think is happening is as the tide swishes across, say, a continental slope is half of this picture, for instance, but as it swishes back and forth across a seamount, what you can see is that you kind of still pull down the isopycnals on one side with the swishing of the tide in the lee, as it were. But that remains kind of trapped to the continental slope and becomes a nonlinear internal, what we call lee waves that are high frequency, unstable, and susceptible to mixing right at the location of generation, as opposed to being able to propagate any further. There is circumstantial evidence for this. Here is some results from Ilka Fur and company. So in the case of the generation of this lee wave, unstable lee wave, what you expect is, first of all, you get some current somehow, which is pushing water off the slope. So in this particular case, it turned out to be a large off-slope diurnal. So once a day, tidal currents pushing water off the slope. So you get these, here we see the sort of off-slope current being quite high, which then, as you can see under 2, pushes down the isopycnals. It pushes down the isopycnals, and this then creates the condition, or rather a hydraulic condition, where the Froude number is raised to more than 1, which is the critical condition for the generation of the lee waves. And these colored profiles here show you that you do indeed, in the red, get high turbulent kinetic energy dissipation associated with this kind of isopycnal deformation. So really, we do think that we are getting these lee waves being generated, and you can see the propagation, or kind of little bit of propagation, of internal solitons as depicted from the satellites. SAR images in this area here. So we do expect these nonlinear features to be present in this location. The other evidence that we have that this may well be happening is from some moorings in this location here, north of the Laptev Sea. And in this case, remember, what we're expecting to see is a dip in isopycnals. Oops, let's go back. A dip in isopycnals. And the dip in isopycnals corresponded with high currents, pushing those isopycnals down offshore. And this corresponded to really high dissipation, which is that red profile here. So those are measured. The dissipation was measured right at the end of this kind of bouncy, kind of high velocity dipping in isopycnals event. This case was not tidally driven. So this is a rather interesting case in which we think it was driven rather by a far-field storm, which I'll explain in a minute. But in relating back to the original aims of our Peanuts project, we were really interested to see if those drove big nutrient fluxes. And so here in the back, what we have, these black and diamonds, show you kind of the background nutrient fluxes that are measured along stream in the Atlantic water. along this pathway. But at this location, on this occasion, you can see that, remember, this is a log scale, we actually had an increase of 1,600% of the nutrient fluxes above the background rates. And that resulted in locally enhanced primary production. And these events are linked to decreasing sea ice. So in terms of looking for an event from the moorings that showed that in an occasion where there was less sea ice, you also had high currents and the pushing down the isopycnals. These are all picked out in different years by the stars. And this is plotted over the kind of sea ice extent for these locations. And you can see that they happen more often when the sea ice is absent than when the sea ice is present, although you still get them when sea ice is present. And so we expect that these mixing events are going to become more and more frequent in the future. And how are they driven? How are they driven? Let me tell you that in a minute. But before that, I should also say there is a background climate change going on in that we're getting the Atlantic water flowing into the Arctic has become warmer and warmer and warmer over time. And that's this red line you can see here. That's the temperature of the Atlantic water. Oh, sorry, my mouse is doing funny things. And as the Atlantic water has increased within the Barents Sea, you can see that the seasonal signal in sea ice has been pushed back. And from about 2005, the seasonal sea ice edge has really kind of retreated north and not come back. At the same time, in this location further along stream, you can see that the depth of the Atlantic water itself is getting closer and closer to the surface. So you have enhanced mixing at the same time at which you are potentially getting changes in the stratification of the Atlantic water, stratification and heat of the Atlantic water. So all these things are compounding in the Arctic. And what we think is happening then, of course, if this is going to be true, if we're getting Atlantification in a process known as where you get warmer and saltier conditions at the surface, reflecting better the Atlantic water properties, this background, we suspect the background gradient may actually move to the right. So in other words, in future, along stream, we're going to get higher background nitrate fluxes in addition to the prevalence or kind of more frequent occurrence of these high mixing events. I should also tell you that in this region here, I had an MSc student who then looked at this quantity, which is the potential energy anomaly using climatology. And what she was able to show is that this potential energy anomaly is the energy required to fully mix your water column. All right, so it's a measure of stratification, and changes in your potential energy anomaly over time are an indication of what mixing has happened to change this quantity. And what we found is that in the Laptev Sea region here, on the shelf adjacent to where we've seen the double diffusion and these happening amidst these isolated synoptic occurrences of extreme mixing, we're actually seeing that if you take the difference between the potential energy anomaly in October and June, this is the cumulative kind of summer mixing on the Laptev Sea. And this is really one of the first bits of data that we have to show that mixing is changing in the Arctic, at least on the margins and on the shelves. Some of you might be interested to know what is happening with that warm Pacific water. Well, that comes in on the western side.
1 minute.
Okay, that comes in on the western side of the Arctic and drives eddies, which we won't talk about here. But I will say that what we've been able to show is that nitrate fluxes, which are here shown in red using models, really kind of does a good job at driving post-summer. So here's summer where you get the spring bloom that happens because of accumulated nitrate over the winter. But post the spring bloom, you really need nitrate fluxes to enhance primary productivity, shown in green after. Okay, so I'm just going to finish and say the Arctic Ocean is warming and melting. we are getting unusual mixing processes, and the mixing will increase as the ice recedes, which means we think we're going to get more greening. Okay, thank you. Should I stop sharing?
Thank you very much, Jung.